In this video, I want to remind you of a technique called factoring by grouping, which is something that you learn about in maybe an Algebra 1 or an Algebra 2 class, probably an Algebra 2 class, when you're dealing with higher degree polynomials. The idea behind factoring by grouping is to make different parts of a polynomial expression connect in the same way. Okay, so let me start out with a really simple example where I kind of explore how you see the factoring by grouping pattern. So let's suppose that we have a cubic polynomial, x cubed plus x squared plus x plus 1. When we factor by grouping, what we do is we take a collection of polynomial terms and we split them up into smaller subgroups. And the examples that I'm going to share with you right now are all going to be based on looking at the first two terms paired together and the last two terms paired together. This isn't necessary, but this is a common way that you see factoring by grouping in lots of algebra problems. So the idea behind factoring by grouping is that there's a connection or a relationship between the first two terms that's also shared by the last two terms. Okay? And the way to see that this relationship is there is to look at these subsets of the polynomial, these individual pairings, and try and factor out or draw out the common factor that each of the pairs of terms shares. Okay, so what exactly do I mean by this? I want you to take the first pair of terms and find its greatest common factor. And then I want you to take the last pair of terms and find its greatest common factor. So if we look at the first two terms, I see that I have x cubed and x squared. Both of these share an x squared. So the first two terms can be written as x squared multiplied by x plus 1. I've taken just the first two terms and I've factored out the greatest common factor from those first two terms. I pulled it out. So these two pieces are equal to one another. If I look at the last two terms and I ask, what's the greatest common factor of x and 1? Well, nothing. X is a variable, 1 is an unlike term, and there's nothing that's shared, nothing that's common to either of those. So the greatest common factor of those two terms is just 1. But even though it's only 1, even though it's not really something interesting, I'm going to write it down explicitly because it'll help you see the pattern for the next step. So if I draw out the greatest common factor here, which is just a 1, now I can make a connection between a pattern that I see in the first two terms and a pattern in the second two terms. Both of these pieces look like a number or a variable or an expression multiplied by x plus 1. Right, so the first two terms, I have x squared times x plus 1. And the second two terms give me 1 times x plus 1. Now that I can see that that x plus 1 pattern is repeated in both of these groups, I can say that that's a common factor, a common pattern to both of these, and I can draw it out. I'm going to use the distributive property in reverse. So rather than splitting something up, I'm going to pull it together by using the distributive property, by kind of factoring out this feature x plus 1 that I see twice. So we have x squared times x plus 1 plus 1 times x plus 1. X plus 1 hits both of these using multiplication. So what we're going to do is say that we have x squared plus 1 multiplied by x plus 1. That is an example, a pretty simple example, of factoring by grouping. We've paired the first two terms, we've factored something out. We've paired the second two terms and we've factored something out there. And when we do that, both of these groupings share the factor x plus 1. We then can use the distributive property in reverse to draw that out and write this in a factored form. Okay? If you wanted to completely factor this, you would then try to apply other techniques to factor, but in this case x squared plus 1 doesn't have any real roots, so this is the fully factored form of that cubic polynomial. So that's the basic idea. We're going to group terms on a polynomial, try to pull out common factors from the groups that we create, and then see if they share a pattern that we could factor out from the polynomial as a whole. Okay? So the next example I'd like to try looks a little bit more complicated, but we're going to use the same basic pattern. We're going to use a cubic polynomial, and we're going to group the first two terms and the last two terms, and then draw out common factors from each. So let's look at 4x cubed minus 2x squared plus 2x minus 1. Okay. So now, if we look at the first two terms and we draw out a common factor from there, I can see that these two terms share an x squared, and they also share a factor of 2. So if I factor out 2x squared from these two terms, we'll be left with 2 times the x that's left over, which is 2x. And then here, since we're drawing out 2x squared, that pulls out all the factors in this term and leaves us with just a 1. So this looks like 2x minus 1. Plus our second two terms. These second two terms don't share any factors. We just have a 2x and a minus 1. So there's no factors kind of left over to take out of a 1. And the x term is not shared. So this second term just looks like 2x minus 1. But now we got what we wanted in the sense that the first two terms, when we factored out the common factor there, we're left with exactly the same expression that we have in these second two terms. Both of them share, both groups share this expression 2x minus 1. So as soon as we see that, we can now factor that out and we'll complete the factoring by grouping process applied to this cubic. So we get 2x squared times 2x minus 1 plus 1 times 2x minus 1. And that completes the process again on this second example. Next, I'd like to show you an example where this process doesn't work, where you don't see the pattern that you need to factor by grouping. And then we'll do one more example where it does work. Okay? So let's try another example. And remember, in this example, the factoring by grouping process is not going to work. So maybe we have x cubed plus 3x squared plus 3x plus 1. Okay? All right, so now if we look at this term, or this collection of terms, if I group the first two things together and try to find all that's shared in theirs, the greatest common factor of these first two terms, I see that they share an x squared. So if we factor that out, this will become x squared multiplied by x plus 3. And in the second terms, they don't seem to share anything. So I can think about this as 1 times 3x plus 1. So when I've tried to group in this way, with this example, the pieces that I end up with, or the expressions that I end up with, are not identical. They're not the same. These don't share an x plus 3. They don't share a 3x plus 1. So because these two pieces are different, you can't factor that by grouping in the way that we just did. Okay? So you can't succeed in factoring by grouping here by putting the first two terms and the last two terms together. That doesn't work. Right? There might be another way to factor this, but we might have to group it in a different way to find that. So now let's do an example where these are not the same. Let's do one last example where this is going to work. We'll get the factoring by grouping to succeed. So let's look at x cubed minus 3x squared, so it's similar to this example that we just looked at, but not identical, minus 3x plus 9. Okay, so we're going to try to look at it by patterning. We're grouping the first two terms and the last two terms, and we'll try and draw out common factors to each. So, in our first term, it looks like we have a common factor of x squared, and if we draw that out, or factor that out, the first two terms, we get x squared multiplied by x minus 3. Okay. In the second term, I see that I have a factor of 3 that's shared. Both of these have a 3 in there. So if I draw that out, we get 3 times negative x plus 3. Now, if we left the expression as it stands right now, we have not succeeded in factoring by grouping because this piece is not identical to this piece. Right? I have a x minus 3 and I have a minus x plus 3. But we actually can factor this by grouping if we work a little harder. If I want these two pieces, x minus 3 and minus x plus 3, to look identical, I need to pull out something more than just their greatest common factor. In the second term, if I multiply by a negative 1, or think about factoring out a negative 1, that will turn minus x plus 3 into the factor, or the piece that we found in these first two terms. That will make those pieces look identical, which will mean that we'll succeed or be able to follow through with this factoring by grouping. So let's go ahead and do that. Let's also pull out a negative 1 from this expression here. So we have x squared multiplied by x minus 3 minus 3 multiplied by, change the sign of the x and change the sign of the 3, x minus 3. Okay? So we're able to group the first two terms together and the second two terms together, and if we draw out exactly the right features, we can make the remainder of those expressions, the factored out bit, identical. Okay? So I have something times the factor x minus 3, something else times the factor x minus 3. And now by using the distributive property in reverse, we can factor this out. And this is another example of factoring by grouping. Okay? So in factored form, this is going to look like x squared minus 3 multiplied by x minus 3. If you want to, you can continue factoring even further. You could think about this as a difference of two squares and factor this into 3 separate linear factors. But this process that we just completed right here, this is factoring by grouping. Okay? All right. That completes this example, or this reminder of what factoring by grouping is all about. Just taking a long expression, organizing it into subsets or sub-collections. Here we took 4 terms, looked at 2 sets of 2 terms, and we try to factor out or pull out those features that leave us with an expression which is identical across the groups that we created. So we get x minus 3 appearing in 2 places. As soon as we see that expression in more than one place, we can use the distributive property to draw it out and factor it into a separate piece.